Hey folks, today we're going to take a quick look at a DNS query using Wireshark. We'll visit the TrainingCity.com website while running the Wireshark protocol analyzer and then filter for DNS traffic. Let's get started. So to begin, we'll open the Wireshark protocol analyzer and we'll start a capture. Wireshark is open. We need to pick the interface that we are using to send and receive TCP/IP traffic. In this case, it's my gigabit wired Ethernet adapter. I'll select that and then start capturing Ethernet frames as they come and go from the computer. Now let's visit a website. We'll just reload the TrainingCity.com site. When that's finished, we'll stop the capture and filter for DNS. Remember, in Wireshark, the filters always have to be typed in lowercase. Click Apply. Now we see a number of DNS queries and responses. We see queries for TrainingCity.com, but we also see queries for other domains. For example, Google Analytics, this domain, Facebook, Pinterest, Vimeo, all sorts of additional domains. We didn't intend to visit any of these websites, Twitter. So why are we querying for A records for all of these domains? To understand that, we need to look deeper into the TrainingCity.com webpage. So here's the page. If you look closely, you'll see that there is Facebook, Twitter, Google+, LinkedIn, Pinterest, Vimeo. All of these links here will be in the HTML code and will require additional DNS queries. A lot of people don't realize that visiting one website can result in many DNS queries to allow the page to populate. If we take a little closer look, open the Firebug add-on to Firefox, we can actually search for these domains in the text. Here we see in the HTML code there is in fact a link for Facebook.com. At this point, a DNS query is needed to find the appropriate IP address. So let's go back and take a closer look at the DNS traffic itself. We'll focus on the query for TrainingCity.com and take a look at what fields are in the domain name system header. So again, we're filtering for DNS. We see the traditional three windows of Wireshark. One listing the various packets, one showing the details of the packet you've selected, and the other showing those details written in hex as a representation of the actual binary code. For details on these three windows, the relationship of the hex numbers to the binary details, you can either attend our Wireshark hands-on workshop or just check out some of the other Training City videos here on YouTube. So here is our initial query looking for what's called the A record of TrainingCity.com. We see that it is a DNS over UDP over IP, in this case over Ethernet. Let's look for a moment at the IP header. The fields in the IP header we've covered in other videos. Let's hone in on the source and destination IP addresses. In this case, the source IP is the machine's IP address, and the destination is the home router, which seems a bit odd. Why would I go to the home router if I need to query a DNS server? Well, in this case, the home router includes a DNS cache available for all the home machines. So when I make a query for TrainingCity.com, the home router will actually go out to a DNS server on the internet, resolve the domain name to an IP address, and then store or cache that information in its own memory, so that if another user in the house, or if I again want to go to the Training City site, it may not be necessary, depending on how long in the future I make this query again, for the home router to actually have to go out on the internet. As a result, I can potentially save time by only having to query as far as my local cache. So, this message went from my machine to the device that I have in my home as a home router. It used UDP, and if we look, the source port is just some large port number. Ports, by the way, are 16-bit numbers. We cover that in the TCP/IP hands-on workshop in great detail. You can see them here as 4 hex numbers, each hex number, of course, representing 4 bits, hence 16 bits. 16-bit number written in decimal notation, the sort of standard numbers that we use, would provide a range from 0 decimal to 65,535. We can see that this is one of those port numbers. These are the hex representation of the bits, and this is the decimal representation of the 16 bits. You could convert this in your calculator if you wanted to. With UDP, the source port, indeed with many TCP/IP transactions, the source port is usually an available port on the machine, not necessarily an assigned or well-known port number. It's at the server that we must use well-known port numbers. So for the DNS server, or in this case the local DNS cache resolver, it is necessary to alert that device as to what service is required, in this case the DNS service. We do that by sending the UDP, DNS over UDP message to the well-known UDP port number 53. My local home router is listening on port 53 for DNS traffic. So at servers we use well-known port numbers to allow client devices like this computer to tell the server exactly what service they want. Do they want Hypertext Transfer Protocol? Port 80. Do they want FTP? Port 2021. Do they want DNS? Port 53. Do they want email? Additional ports that are well known. So this message goes from my computer, some available port number, in this case 56144, to the local DNS server, if you like, local DNS cache of the server, port 53. Now, the machine itself will, the home router will receive this message, and it will then open and look at the DNS query. And in this case, we see that there's a transaction ID tracking the DNS message. There's a series of flags in DNS. In this case, only one flag is set, and it's recursion desired. Do query recursively. So what I'm asking is that if you don't know the answer, go to the next DNS server and look for the answer. This has got one question, one request. And if we look closely at the query itself, it says, I'd like to know the A record for TrainingCity.com class internet, meaning TCP/IP. So this is the query. We'll cover some of these details in the DNS class. Well, we'll cover all of these details actually in the DNS class. But for now, we see that it is recursion desired, and it's a request for an A record for this domain. Let's look at the response message that comes back from the home router. We see that this is coming from port 53, going to my port 56144, coming from the server's IP address to my IP address. And when we open the DNS message, we see that it is a same transaction ID. And if we look here, we see that the response flag has been set. The recursion desired flag is continues to be marked, and the recursion available flag is marked. the question is repeated in the response message so that you know this is in fact the question you asked. So let's take a look at the query. There was the original query. Now we see the answer. And if we look, the answer says TrainingCity.com's A record is the address 50.62.72.47. There's a time to live, a data length telling you how many bytes are contained in the address field, in this case 4 bytes, and then the actual answer. So that is a brief overview of the fields you will encounter in a DNS response, a DNS request, and a DNS response. Note that DNS travels over UDP, and it uses port 53. DNS can be sent over TCP, but for a variety of reasons that we cover in the TCP hands-on workshop, it's not efficient to send DNS over TCP under almost all circumstances. So we saw the query, and we saw the response. We see other queries associated with this visit to the Training City site that may be a bit surprising. They're occurring because they exist in the HTML code itself, and therefore a series of DNS queries is needed to complete the population of the TrainingCity.com page. And this is very typical of modern web pages that you'll visit. You may very well find that you are doing 5 and 10 and 15 DNS queries to allow for a page to be populated. All the more reason for these DNS caching capabilities in your home router or in your enterprise services, so that you do not need to do individual queries across the internet looking and tracking down all of these IP addresses. Finally, what we have been searching for and receiving is queries and responses for what are called A records. We're requesting an A record. Next time we'll take a look at how do you query for a mail server, what's called an MX record, and how do you do queries for IPv6 using what's called a quad A record, and then also how do you query for additional services such as a SIP server. Thanks. This has been a quick overview of DNS and DNS query and response from Training City. Have a great day.